Good afternoon. In yesterday's class we started with theory of integers. In that we discussed some of the what is mathematical induction, and also we discussed some of the examples related to mathematical induction. Today we will discuss some of the examples related to induction. Show that the sum of the first n odd integers is n square. You know that if you take if n is equal to 5 numbers, odd integers starts from 1, 3, 5 and 9. If you sum of the 5 integers, first 5 integers, that is 1 plus 3 plus 5 plus 7 plus 9, we can easily added that you get 25. That is same as 5 square. You know that n is equal to 5 means that is 5 square. This is a simple example, and formally we show that for all n, p of n, where p of n can be written as I running from 1 to n 2i minus 1. You know that sum of n integers 1 plus 2 plus 1 plus 3 5 etc. using how to write 2i minus 1 means, you know that 1, 3, 5 etc. it is an arithmetic progression. You know that this can be written as a plus n minus 1 into d. Here a is the first digit, n minus 1, the d is the common difference, that is 2, then you get here 2n minus 2, here 1, then you get 2n minus 1. This is the function usually we are written here, that is here this 2i minus 1 means that is 2n minus 1 is the nth term of the series. Here in place of I we are written started from I running from 1 to n, that is 2i minus 1, that is equal to n square. How to show in the mathematical induction? First we show that in a base case. What is base case? First we started with if p of 1 is true. In this function what happens here? If you put n is equal to 1, that become p of 1, summation I running from 1 to 1 means you get only one number, that is 2 into 1 minus 1, that is equal to 1, and n squared, that is also 1, then you get 1 equals 1, that is left hand and right hand both are same, means that it satisfies the base case. Next we show that the induction hypothesis. What is induction hypothesis? Assume that it is true for k, thus we assume that p of k is true, or that I running from in place of n, here we change to k, that is 2i minus 1, then n become k square. What is to prove here? We can prove that p of k plus 1 is also true. Note that we do not yet know if this is true or not. You must remember, in the induction step we show that it is true for k plus 1. We want to show that here in this k, we want to show that k plus 1 is also true. Recall the induction hypothesis. We started with that k, this is true, we assume that this value is true for that I running from 1 to k, 2i minus 1 is equal to k square. The proof of inductive step is, that is I running from 1 to k plus 1, 2i minus 1 equals k plus 1 the whole square. Means here this is the next term, what is that, 2 times in place of I k plus 1 minus 1, then here we can write up to k term, we can write it here, the k plus 1th term is 2 times k plus 1 minus 1 plus you get this, that is if you expand this, that is k plus 1 the whole square means a plus b the whole square formula, that is a square plus 2ab plus 1 means here k square plus 2 into k into 1 plus 1. Next, if we simplify that, this is same as the base step. What is that? We assumed step, that is k square, then 2 times k plus 1 minus 1 into this is same as this, we substituted here, then that is same as k square plus 2k plus 1 in the left hand side as well as right hand side. This is one of the deductive procedure. then what did we shown? Here we what shown that base case P of 1 is true. If P of k was true, then P of k plus 1 is also true. That is, P of k implies P of k plus 1. And we know that it is true for P of 1 because P of k tends to P of k plus 1. If it is true for P of 1, then it is true for P of 2, because P of k tends to P of k plus 1. If it is true for P of 2 also, then it is true for the next integer, that is P of 3. Similarly, because of P of k tends to P of k plus 1, if it is true for P of 3, then it is true for P of 4. That is the induction. Then because of P of k tends to P of k plus 1, if it is true for P of 4, then it is true for P of 5. And similarly, it goes to onwards to infinity. Thus, it is true for all possible values of n. In other words, we show that here P of 1 and for all k, P of k tends to P of k plus 1 tends to for all n P of n. This is the tautology statement you already seen in your logic. The idea what is behind in this inductive proof? Show the base case, show the inductive hypothesis, manipulate the inductive step so that you can substitute in part of the inductive hypothesis. Show the inductive step. In the second induction, this is another example we are giving here. Show that sum of the first n positive even integers is n square plus n. We rephrased this problem as for all n, P of n, where P of n is equal to summation I running from 1 to n. You know that the even integers means 2, 4, 6, etc. 2, 4, etc. means if you take 2 as a common factor, then you get 1, 2, 3, etc. The sum of n integers, you know that that is n, then here 2 times n will be there, you get that is P of n can be summed written as I running from 1 to n, that is 2 times I. That is, if you put I is equal to 1, you get 2 plus 4 plus 6 plus etc. That is 2n is the nth term. That is equal to n square plus n. Here the proof, there are 3 parts will be there. One of them is base case, inductive hypothesis, then inductive step. What is base case? Show that it is first P of 1 is true. Here P of 1 means in place of n you are putting 1 here. I running from 1 to 1, 2 times I is equal to I squared plus 1 squared plus 1. Here this is only one number will be there, that is 2 only in the left hand. In the right hand 1 plus 1 is also 2. This implies the base case is true. Next we go to inductive hypothesis. What is inductive hypothesis? We assume that it is true for k value, then we shown that P of k plus 1 is also true. Here in place of n, P of k is equal to I running from 1 to k, 2i equals k square plus k. Inductive step, show that P of k plus 1 equals I running from 1 to, in place of k here k plus 1, next term 2i, then this become k plus 1 the whole square plus k plus 1. We recall our inductive hypothesis, that is P of k, it is true, assume that it is true, I running from 1 to k, 2i equals k square plus k. Then we start with the what is to prove, that is I running from 2 k plus 1 to 2i is equal to k plus 1, in place of k we have substituted k plus 1, that is k plus 1 the whole square plus k plus 1, that is in the right hand side. In the left hand side, this can be rewritten as 2 times we can split this 2 times k plus 1 this side plus the remaining is here I running from 1 to k to I. This is the next term we are taken outside. Then what is this? This is assumed that it is true that value is k square plus k. We can substitute it here. Then we get 2 times k plus 1 plus k square plus k. Then if you simplifying this is substituted value. Next, if you simplifying that, you get k square plus 3k plus 2 in the left hand side. Similarly, in the right hand side also k square plus 3k plus 2 means it is the inductive hypothesis if p of k plus 1 is also true. Means we manipulate the k plus 1 case to make part of it look like the k case. When then replace that part with the other side of the k case, that is peak of k summation I running from 1 to k 2I equals k squared plus k. Then I running from 1 to k plus 1, this we get the result we shown in the previous slide, that is I running from 1 to k plus 1 the whole square k plus 1. Here we substituted here, we get the result for that. Next we give another example related to induction. Show that summation I running from 1 to n I squared equals n into n plus 1 into 2n plus 1 by 6. We are frequently using this formula. You know that 1 square plus 2 square plus 3 square etc. up to n square, the formula is n into n plus 1 into 2n plus 1 divided by 6. Here how it is true we are shown. Further, here also there are 3 cases. One of them is base case, induction step, then induction hypothesis. Base case means put n is equal to 1. If you 1 means I squared, that is 1 square. In the right hand side 1, if you put n is equal to 1, 1 into 1 plus 1, 2 into 1 plus 1, then if you simplifying this you get 1 equals 1, means it satisfies the base case. Next, induction hypothesis means replace n to k here, I running from 1 to k, I squared is equal to k times k plus 1 into 2k plus 1 divided by 6 is true, assume that it is true. Next we show that, what is to show, I running from 1 to k plus 1 I squared is equal to, in place of k we replace to k plus 1, k plus 1 k plus 2 into 2k plus 3 divided by 6. Here in the I case we can reshift here, that is summation k plus 1 the whole square, here k plus 1 the whole square plus this one, it is splitted, then last term can be taken outside, the remaining is summation I running from 1 to k I square. What is this? This is same as k into k plus 1 into 2k plus 1, that is that value is true, this is true. Then we substituted here k into k plus 1 into 2k plus 1 by 6, we substituted because we know this rule, we substituted here. Then that value, if you simplifying this, take LCM and simplify, that is 6k plus 1 the whole square plus k into k plus 1 into 2k plus 1, then that is both are left and right hand sides are equal, that is 2k cube plus 9k cube square. If you simplifying this, multiply these 3 values as well as expanding this, that is a plus b the whole square, you get 2k cube plus 9k square plus 13k plus 6. Similarly, in the right hand side also the multiplication product of k plus 1 k plus 2 into 2k plus 3 become 2k cube plus 9k square plus 13k plus 6. Next, the third induction again, that if you take a different value instead of what is the induction hypothesis was wrong, all the hypothesis is correct because we know that result that is correct. Sometimes instead of in the previous slide, yeah, this is the formula I running from I squared equals k into k plus 1 into 2k plus 1 by 6. Instead of that, if you take here 2n plus 2 more than another value, then what happens in the induction base? In the first step itself, the base case, if you put n is equal to 1, this become 1 square. 1 square equals 1 into 1, you get that 1 is not equal to 7 by 6. Definitely this formula is not true. But however, we can try, this may be true in the inductive case. But let us continue anyway. The induction hypothesis become, we taken that this is true, the inductive shown that summation I running from 1 to k plus 1 I square, then replace k to k plus 1 in the right hand side also. Then if the simplification, then here in the left hand side, then previous term, that summation I running from 1 to k squared is equal to k plus 1 the whole square. Then the simplification part is this one. Next, this value is, we have taken summation I running I squared is equal to k into k plus 1 into 2k plus 2 by 6. Because this is the value assumed, we substituted here, left hand and right hand are equal or not, you can check out. Take LCM here, then 6 times k plus 1 the whole square, k into k plus 1 2k plus 2, then here 6 become cancel, then the product of these 3 and these 3 and this one, the simplification of a plus b the whole square term, you get 2k cube plus 10k square plus 14k plus 6 in the left hand side. In the right hand side, you get the first term is equal, second term is also equal, but in the third term represent 14k, but here in the right hand side 16k plus 6 will be there. These two are not equal, means the formula is wrong. Now we give the another example related to induction. Show that n factorial is less than n power n for all n is greater than 1. I told in the last class itself, if the induction step, if it is starts from 1, then you can start with 1. If it is given the restriction, if n is greater than 1, then you can start with the base case, that value only. What is base here? In the base case, n is equal to 2. N is equal to 2 means here 2 factorial is less than 2 square. 2 factorial means 1 into 2, the value is 2, less than 2 square means definitely that value is 2 is less than 4. Then that base case is satisfied. Next, we assume that the induction hypothesis, in place of n we replace to k, that is k factorial is less than k power k is true. Then we are showing that k plus 1 factorial is less than k plus 1 to the power of k plus 1. Here the inductive step, we start with the left hand side of this, k plus 1 the factorial is equal to, that can be written as k factor 1 into 2 into 3 etc. up to k factorial will be there. Then that can be written as k plus 1 into k factorial. Then we know that k factorial is less than k power k. Then this can be written as less than, using this condition here, less than k plus 1 into k factorial is less than k power k. Then this become less than k plus 1, this is k plus 1 to the power of k. Definitely this one value k plus 1 to the power of k is greater than this value. Then k plus 1 to the power of k, then this become k plus 1 to the power of k plus 1, means k plus 1 factorial is less than k plus 1 to the power of k plus 1 means this true for p of k plus 1 case. Now we prove the induction procedure. You already familiar with this. Now we discuss the induction hypothesis. Now we will discuss the second part of this chapter is recursive definitions. What is recursive definition? That is, if you know the n value, then we get the previous ones, then we get the recursive for rules. A recursive rule or a formula for an, nth term, in terms of an minus 1, an minus 2, etc., or a formula for an plus 1 in terms of the previous ones, an minus 1, etc. For describing a sequence, two methods are commonly used. One is explicit method, another one is recursive method. Here we are concentrating on recursive methods. In a recursive definition of a sequence, the number of terms which are required to be specified explicitly depends upon the recursive rule used. If the recursive rule requires the use of k number of preceding terms for obtaining a new term, then the first k terms of the sequence must be indicated explicitly in the first part of the definition. Here we note that the recursive definition of the sequence E equals an, this is a suffix n, where a1 equals 2 and an is equal to a times, actually this is the recursive definition here, a suffix n, and a1 equals 2 and an can be represented as an minus 1, this is the recursive, plus 2, here n is an integer, n belongs to integer, this is the function. Consider the recursive rule requires the use of only the preceding term an minus 1 for obtaining a new term an, using the previous term and we get the an, and it is for this reason that only the first term of E is indicated explicitly. Now we will give some examples related to recursive definition. Obtain a recursive definition for the sequence an in each of the following case. First, here an equals 5n. Here an equals 5n will be there. An equals 5n. In that, first what is it we needed? The first one, put n is equal to 1, you get a1 is equal to 5, and if you put n is equal to 2 here, you get a2 equals 5 into 2, 10. Similarly, a3 means 5 into 3, that is 15, etc. You get a4, if you need a4, that is 20. Then we can write it as a1 equals 5, and this an can be represented as an minus 1, 1 is less, that is an minus 1 plus the first term plus 5. This is the recursive formula for that, and also we start, because already we put the first one, n is greater than or equal to 2. This is the recursive function. Similarly, in the second one, an equals 6 power n will be there. Put n is equal to 1, you get a1 equals 6 and a2 equals 6 square, a3 is equal to 6 power 3, and a4 is equal to 6 power 4, we can rewrite this as a1 equals 6 and an plus 1, the n plus 1th term equals 6 times an. If you put a1 n is equal to n equals 1, you get 6 here, and n is equal to 2, you get 6 times 6, that is 6 square will be there, then 3 you get the previous one. This is the recursive formulas. In the similarly here an, in the third problem, these are simple recursive function, an equals 2 minus minus 1 to the power of n, and another one is an equals 3n plus 7. Always we can start with here first value a1, if you put n equals 1, you get 2 minus of minus 1 to the power of 1, then you get a1 equals 2 times minus 1 to the power of 1, that is minus 1 to the power of 1 is 1, then 2 minus of minus is plus, you get 3. That one we represented there, a1 is equal to 3, and if you put n is equal to 2 here, a2 equals 2 minus minus 1 to the power of 2, that is minus 1 into minus 1 is plus, you get 2 minus 1, you get 1. Similarly here a3 equals what happens, 2 minus minus 1 to the power of 3 will be there. Again here even and odd terms, if 1, 3, 5, 7 etc., you get minus sign, you get 3. Otherwise you get the other one is 3 and 1, 3 and 1 will be recurrence, you get it that. That's why we can take it as an minus 1, sorry an plus 1 minus an. The difference, then you get an plus 1 is here, 2 become here an means 2 will be there, 2 become cancelled, 2 minus minus 1 to the power of n plus 1 minus here 2 minus minus 1 to the power of n will be there. Here 2 become cancelled, you get here minus of minus 1 to the power of n plus 1, minus of minus into minus is plus here, then you get minus 1 to the power of n, then you get minus 1 to the power of n is a common factor, you get here 1 plus minus 1 the whole square, you get that is 2 times minus 1 to the power of n. Means if you simplifying this, that is an plus 1 equals an plus 2 times minus 1 to the power of n. This is the recursive formula for if an equals 2 minus minus 1 to the power of n using the previous terms. And in the fourth problem here, that is a1 equals 10, and put a2, if you put n is equal to 2 you get 13, and a3 becomes 16, and a4 it become, you know that the problem here, that is 3n, an equals 3n plus 7. Always you can start with put 1 and 2 and 3 value. What about the fourth one? What are the things can be observed there? Here first we put n is equal to 1 here, n equals 1 means 3 plus 7, that is 10. If you put n is equal to 2 here, that is 2 into 3 is 6, 6 plus 7 is 13. If you put 3 here, 3 into 3 is 9, 9 plus 7 is 16. Similarly if you put 4 into 3 is 12, 12 plus 7 is 19. This can be written, first term is 10, an equals 10 plus 3. If you add here, you can observe here, this is 10 is there, 13 is there, here 16, means each term containing the difference is 3, 3, 3. Then an can be written as an minus 1 plus 3 for n is greater than or equal to 2. This is the recursive definition of the given sequences. These are the elementary examples we are given to recursive definition. The next type problem, find an explicit definition of the sequence defined by recursively by. First one is a1 is equal to 7, the first value is given, and an equals 2 times an minus 1 plus 1 for n is greater than or equal to 2. Here I will show the first one. The second one is similarly, you can do it yourself. The first problem, by repeated use of given recursive formula. Here an equals 2 times an minus 1 plus 1. Using that, an can be written as 2 times an minus 1 plus 1, means again here this an minus 1 can be replaced to, in place of here an is there, an equals 2 times an minus 1 plus 1 will be there. What about an minus 1 here? An minus 1 is 2 times a times, in place of n minus 1 means n minus 2 plus 1. This one we can substitute it here, that is 2 times of 2an minus 2 plus 1. Similarly, what about an minus 2? 2 times an minus 3 plus 1. Similarly, an minus 3 equals 2 times an minus 4 plus 1. These function recursively, you can repeated use of recursive definition in each step, means here we used here 2 in this an minus 1 we use this, again here an minus 2 we substituted here. Then what is the simplification here? The simplification is here we are substituted 3 times 1, 2 and 2, 2 power cube an minus 3 plus, here you can observe 1 plus 1, 2 will be there, 2 into 2, here also 2, that is 2 square plus 2, 1 plus 1 is 2 plus 1. You can observe here this is 2 cube plus an minus 3 plus 2 square plus 2 plus 1. If you going similar way, in n minus 1th term become here 2 power n minus 1, a of n minus of, in here 3 is there, that replaces to n minus 1 plus here 2 power 2 1 less of this value means here n minus 2, n minus 1 here n minus 2 plus 2 power n minus 3 plus etc. 2 plus 1. If you are observing here, this is 1 plus 2 plus 3 plus, means you know the geometric series, you know that geometric series 1 plus a square plus etc. that is equal to, what is that, into infinity is 1 minus, sorry, a power n, sorry, 1 plus r square plus etc. that is 1 by 1, here a is not there, 1 is there, 1 by 1 minus r is the n term to infinity. But here it is up to 2 power n is there, then that can be written as 1 minus r power n, here also 1 minus r to the power of minus n will be there. You can substitute the geometric series for this. If you substituting the geometric series up to this, that become 2 power n minus 1 divided by 1 minus r, denominator is 1 minus r, 1 minus r is here 2 power n minus 2 plus 2 power n minus 3 plus etc. plus 2 plus 1 will be there. This function become here, that is 2 power 1 less, that is 2 power n minus 2 minus 1 divided by r is 2 here, 2 minus 1, that is 2 to the power of n minus 1 minus 1 divided by 2 minus 1 is 1. This one we are substituted here. And also here the first value is given, a1 equals 7. a1 is 7 means this is 2 power n minus 1, here also 1 2 power n, 7 plus 1 is 8, 8 times 2 power n minus 1 minus 1. This is the recursive definition of the repeated use of, you get the, similarly you can do it yourself this problem. Next we will discuss some of the important numbers, that is Fibonacci numbers. The Fibonacci numbers defined recursively by f0 equals 0, f1 is equal to 1 and fn equals fn minus 1 plus fn plus 1 for n is greater than or equal to 2. Here in this Fibonacci numbers, we can find the Fibonacci numbers from f2 to f10. You can find f2 to f10 means in place of 2 here, n is equal to 2, what happens? You get first f2, because in between values we cannot find. This is a sequence, recursively we can find the values. If we need f5, we cannot find f5 directly. In that time we can first you can find f2, f3, f4 etc. That is recursively. In this function f2, what is f2? f2 become here, this is the formula fn minus 1 plus fn plus 1. Fn minus 1 is means put n is equal to 2, 2 minus 1 is 0, here 1 plus 1 is here 0, we are putting f2, then 2 plus 1 is 3 here. f2 equals f1 plus f0. I think here the mistake is there. This is fn minus 1, then fn plus 1. Okay. Here first we start with 2, f2 equals f1 plus f0. f1 is given, that is 1, 1 plus 0 is equal to 1. Then f3 become f2 plus f1, that is 1 plus 1, that is 2. f4 is f3 plus f2, we already known f3 value, that is 2. f2 means that is also known, that is f2 is 1, substituted you get 3. Similarly we can find the f5 is 5, f6 is 8 and f7 is 13. Recursively we can find up to f2 to f10 values, that is 1, 2, 3, 5, 8, 13, 21, 34 and 55 are the sequence of a Fibonacci numbers. In this Fibonacci numbers, we can prove that if f0, f1, f2 are Fibonacci numbers, prove that I running from 1 to n, fi square equals fn into f of n plus 1. fi the whole square is fn plus f of n plus, means nth term and n plus 1th term, the multiplication for all positive integers n. Here we started with the base case. What is that? First we note that if I running from 1, that is fi square means f0 square plus f1 square. f0 is 0 and f1 is 1 here, then 1 equals f1 is 1, f2 is also 1, 1 into 1 is 1, then f1 and f2 are 1, you know that, then this verifies the base case by induction proof we are giving here. Next we assume that the result is true for n is equal to k plus 1. n is equal to k plus 1 means first we know that, assume that I running from 1 to k, fi square equals fk into f of k plus 1 is true. Consequently we are proving that I running from 1 to k plus 1 equals fi square equals fk plus 1 into fk plus 2. That is our aim. Here we started with, then we can split this, I running from 1 to k, fi square plus fi I in place of I, k plus 1 the whole square. Then this is already assumed that this value is known, that is fk into fk plus 1, fk into fk plus 1. In these two we can take a common factor fk plus 1, that is fk plus 1 into the remaining is fk plus fk plus 1. This is Fibonacci sequence. We know that fk into fk plus 1 is fk plus 2. Then in these two function, if you add you get f of k plus 2. Then this result is true for n is equal to k plus 1 case also. Means by induction hypothesis, this formula, the Fibonacci rule, this formula is fi square is summation I running from 1 to n, fi squared is equal to fn into fn plus 1. The next is another famous numbers. The Lucas numbers are defined recursively by L0 equals 2, L1 equals 1 and Ln equals Ln minus 1 plus Ln minus 2 for n is greater than or equal to 2. Here also we can start with L is equal to, first we put n is equal to 0 here, n is equal to 2 here because it starts from 2, because we find L2 to L10 means 2 to 10. Here also same procedure we adopted in the Fibonacci numbers. Here in the Lucas numbers, if you put n is equal to 2, L2 equals L of 1 minus 1, that is L0, you get 2. Here 2 minus 2 is 0, you get L0 here, you get here 1, L1 plus L0. L2 equals L1 plus L0, you get 3. Similarly, L3 is L2 plus L1, you get 4. L4 is L3 plus L2, you get 7, L5 equals 11, L6 equals 18, L7 is equal to 29 and L8 equals 47 and L9 equals 76, etc. We get the sequence of L2 to L10. If you write it in a number, that is 3, 4, 7, 11, 18, 29, 47, 76. That sequence is known as the Lucas sequence. If you write it in a numbers in a sequence, we say that it is Lucas numbers. Next is if FIs are the relation between Fibonacci and Lucas numbers. If FIs are Fibonacci numbers and LIs are Lucas numbers, or prove that 5 times Fn plus 2 equals L of n plus 2 plus Ln for n is greater than or equal to 0. Here also we prove by induction method. First we put in base cases n equals 0, because it starts from n is greater than or equal to 0 means we put n equals 0 first. For n equals 0 and n is equal to 1. Here the formula is 5 times f n plus 2 equals L of n plus 4 plus Ln. And also you know that the Lucas formulas, here we can use, put n equals 0 here. N equals 0 means this becomes 5 times f2 and here L of 4 plus L of here if you put n is equal to 0, L0 and L4 will be there. L4 minus L0 equals 5 times F2, then L5 equals, you know the value of L5 we already find, that is 7 and L4 is 7 and L5 is 11. We already calculated in the previous cases. Then we use that. Here L0 is 2 and L1 equals 1, then L4 equals 7, L5 is equal to 11. And also we know that F2 is equal to 1 and F3 is equal to 2. Means if we substituted there, that values L2, L4 minus L5, L0 equals 5 F2. L4 is 7 minus L0 is 2 and 5 into F2 is 1. We know that 5 equals 5. This the base case is true. Similarly, L5 minus L1 equals 5 times F3. We know that F3 value, that is 2 and L5 equals 11 minus here, that is L1 is 1, then you get 10 equals 10. Means if n equals 0 and 1, both the results are satisfied. Means base rule is satisfied. Next we assume that the result is true for n is equal to 0, 1 to k, where k is greater than or equal to 1. Here then we find that L of k plus 5 minus L of k plus 1, here L of n plus 5 means next number we used here. We assume that Here L of 5, the next number minus, we can take a right hand step of that, L of k plus 1. Here L of k plus 5 can be written as in the Lucas numbers, that is L of k plus 4, previous number plus L of another one, L of k plus 4 plus L of k plus 3, minus here this can be written as L of k, next number is L of k plus L of k minus 1. Using this, the induction here L of k plus 1 and this and these two combinations we can use, and we get a L of k plus 4 minus L of k minus, sorry, here minus into minus is plus here, then L of k plus 3 will be there. L of k plus 3 can be written as L of k minus 1 plus 4 minus L of k minus 1, because 5 can be here, 3 can be written as k, because 3 can be here, k minus 1 term is there, that is why we adjusted this as L of k minus 1 plus 4. Then what is this? This is 5 times f of k plus 2 is the formula. Then again what is this? This is same as f of k plus 1. Again here 5 will be there, 5 times f of k plus 2 plus f of k plus 1, by Fibonacci numbers this can be written as the f of k plus 3, means L of k plus 5 minus L of k plus 1 is 5 times f of k plus 3, means this result is true for the induction step, inductive step, that is k plus 1 step. Next we discuss the Eulerian numbers. For integers m and k, the Eulerian numbers a, m, k are defined recursively as follows. If a 0 0 equals 1, a m k is equal to 0 for k is greater than or equal to m greater than 0, and a m k equals 0 for k is less than 0. And a m k, this is the recursive formula of Eulerian numbers, that is m minus k times a of m minus 1 k minus 1 plus k plus 1 into a m minus 1 comma k for 0 less than or equal to k less than or equal to m minus 1. Here you can similarly in the Lucas and Fibonacci numbers we find L5, L2, L3, L4 up to 10. Similarly here also determine the values of a of m comma k for 1 less than or equal to m less than or equal to 5, means you can find m starts from 1 to 5 and k starts from means less than 1 means 0 to 4, that is the values. Here for 0 less than or equal to k m minus 1 we have the definition a m comma k equals m minus k into a m minus 1 into k minus 1 plus k plus 1 into a m minus 1 into k. This is the definition, Eulerian number. When m equals 1, definitely k equals 0 and 1, we get a of 1 comma 0, substitute m is equal to 1 and k equals 0, you get a of 1 comma 0, that is 1. And also 0 comma minus 1, a of 0 comma minus 1 is 0 and a of 0 0 is also 1, that is given. When m equals 2, this expression holds good for k equals 0 and 1, we get a of 2 comma 0, 2 minus 0, a of 1 and here minus 1, 0 plus 1, a of 1 comma 0, that is a of 1 comma 0, you know that a of 1 0 you get 1. Similar, a of 1 0 is 1, then similarly we can find a 2 comma 1, you get 1. If m is equal to 3, you get a 3 comma 2, that is 1, a 3 comma 1, that is 4, and a of 3 comma 1 you get 1, because in the recursively we get each step we get the different values. Similarly we get the a 4 comma 3, a 4 comma 2, a 4 comma 1 and a 4 comma 0. Similarly we get the if m is equal to 5, A5 comma 4 is equals to 1, A5 comma 3 equals 26 and A5 comma 2 is 66, we get the values. These are some of the important recursive formulas we discussed. Thank you. In next class we can discuss the Ackermann numbers and details.